Greetings everyone. In our previous video we have discussed about average velocity, instantaneous velocity and gave the definition of derivative of a function. In this video we will see the geometric interpretation of derivative, but before that we have to understand slopes and rate of change. Now when we say rate of change of A with respect to B, we mean that how much of the quantity A has changed when we make a change in the quantity B. Of course A depends on B, and mathematically we say A is a function of B. So velocity can be viewed as the rate of change of distance with change in time. Rate of change occur in other applications too. For example, a microbiologist might be interested in the rate at which the number of bacteria in a colony changes with time, or an engineer might be interested in the rate at which the length of a metal rod changes with temperature. Here, our objective is to find the meaning of rates of change of y with respect to x, when y is a function of x. Now, when y is a linear function of x, which actually gives a straight line, then rate of change of y with respect to x is a constant, which means that, whenever we move a certain distance along the line, the ratio of the change of y and the change of x is constant. Also, we can see that, till the distance along the line is same, the ratio remains constant. But this rate of change may not be constant for any arbitrary curve. Here, as the curve increases or decreases rapidly, an equal change in x produces a larger change in y than comparing to the other regions of the curve. Now, considering the function f to be linear, we move along the line to get a change in x and a change in y. This change is represented by the small triangle, which we call delta. So, the ratio of delta y and delta x is a number, m. Here, m is called the slope of the given line. The slope of the line measures the rate of change of y with respect to x, when y is a linear function of x. The slope of a line, m, not only measures the rate of change but also gives a sense of direction of the line. The slope can be positive, negative or zero, depending upon the orientation of the line. Now, if we move certain distance from the point P, along the positive x direction, and then if we have to move in the positive y direction to meet the point Q on the curve, then we consider the slope of the line to be positive. In the second case, for the negative slope, we see that when we move a distance from P in the positive x direction, we have to move in the negative y direction to meet the point Q on the curve. Finally, for a horizontal curve, for any change in positive x direction, there is no change in the y direction, so we say that the slope of a horizontal line is 0. If we consider the slope-intercept form of a non-vertical straight line, and consider the coordinates of any 2 points on the line, as shown in the figure, then the differences, y1 minus y0 and x1 minus x0, is the change in y and x respectively. If y equal f of x, then the last equation gives the slope of the line, whenever f is a linear function. As we have seen earlier, the slope of a non-vertical straight line is constant, but it is not the case for any other arbitrary curve. Slope is different at different points on such curve, and the slope of the curve at any particular point is actually the slope of a tangent drawn at that point. The reason for this fact will be discussed in our next video. So, to define the tangent at any point on the curve, we need a mathematical tool which we have already discussed, which is the concept of limit. Suppose we want to draw a tangent at the point P on the curve. For that, we will take another point Q different from P, and draw a straight line passing through them. This line is called the secant line through P and Q. Now, if we move Q closer and closer to the point P, then we can see that the secant lines are approaching a limiting position. This position is actually a line, which we will consider as the tangent line at P. From this approach, we can say that the tangent line is actually a limit of the secant lines. The previous procedure to obtain the tangent line is repeated here, but with a bit more details. We can see from the diagram here, the x-coordinate of point P is x0, and the x-coordinate of point Q is x1. Now, there are two things to observe here. First, as the point Q approaches the point P along the curve, x1 approaches x0. Second, remember the slope of a line that was obtained before, which we will use to get the slope of the secant line here. Now, we have seen that as Q approaches point P, the secant line approaches the tangent drawn at point P. So, from this we can conclude that, as x1 approaches x0, slope of the secant line approaches the slope of the tangent line, drawn at P. The last expression in the box is important. To get rid of the arbitrary point x1, and to obtain a well-known expression, we replace the change in x by h. Now, the left-hand side of the final expression is actually the derivative of the function at x0. Our final goal is obtained with this single line. So, the derivative of a function at any particular point is the slope of the tangent drawn at that point. F' is also function, whose domain is same as that of the function f, where the limit of the above expression exists. Sometimes it is helpful to think f' as machine, which takes input as points from the curve where we can draw tangents, and spits out the slope of the tangent at that point as the output. From the discussion we have observed that the slope of a tangent is actually a limit, and while we know that limit sometimes does not exist for this reason, we give the following definition. Now, the slope of a tangent is a two-sided limit, which will exist if and only if both the one-sided limits exist and are equal. We name these one-sided limits as the left-hand derivative and the right-hand derivative. We consider two cases for which the slope of the curve at any point may not exist. These two cases are the singular points and the points of vertical tangency. For the first case, we consider the curve here, and suppose we wish to know the slope of the curve at the corner point, whose x-coordinate is x0. Now, we consider two arbitrary points on the curve, and draw the secant lines passing through them. As these points approaches the corner point, the secant lines approaches to two different tangents, giving us two different slopes at the same point. So, the left and right-hand derivative at x0 are equal, hence we say that the slope at the corner point does not exist. For the second case, we consider a different curve. Suppose we want to find the slope of the curve at this point. As before, we consider another point, and draw the secant line passing through them. In this case, the tangent at x0 is a vertical line, whose slope is plus infinity or minus infinity, approaching from the left or from the right. Hence, again we say that the slope at the point of vertical tangency does not exist. Thank you.